Now that I'm about to mention it, I know I'm going to screw up at some point and forget to record. And then I know it's going to happen, but it hasn't happened yet this term, so. Oh, hey, what the heck? Wow, cool. Okay. Did not know I could accidentally swipe my thumb and see other notes. Pretty cool. So, oh yeah, what I did, you can pretend that you didn't hear me, but I changed the due date till Sunday night for the quiz because wanted you guys to have a little bit of time. I saw, I know it's a busy time right now, so just to give you a little bit more time. And
it's gonna be a fun week next week.
Yeah, I know.
I've got two tests on Tuesday, and then the test for this course on Wednesday. So that's gonna be fun.
Jam-packed first half of the week. Just cram it in. I know our test actually caught me surprised this morning. It's like, it's next week? The heck? Because my pre-calc test is the following week, so I just had all my tests lumped together. Anyways, we can move it if you want. I just don't like moving it because from the beginning of the term, I've been saying this is when it is. But we can bump it, but then we would have related rates on there, and
I'm not fussed.
Really hard. So I think we should just keep going.
Yeah, I'm gonna lose my mind anyway. I might as well do it all at once.
That's the spirit. Yeah. So quiz number 6, and I don't know why I didn't bump those assignments until Sunday as well, but I'll do that after class. So quiz number 6 is moved to Sunday night, just in case you need a little bit more time. Okay, so should get into it. Just a little bit of review. So we started implicit differentiation. Implicit differentiation, where we have, oops, that's not an O. There. Where our functions are not explicitly in terms of y, but we have kind of y baked in with x's, right? So implicit y is, sorry, the function is not explicitly solved for y. Instead, y is incorporated with the x's. Oops. So what we had to do, right, is we differentiate our x's just like we normally would, right? Usually the power rule or the chain rule or whatever. And then when we come across our y's, what we do is, and this is kind of the unofficial version, at least how I think of it in my head, what we do when we get to a y is we differentiate it like we usually would, but then we always have to multiply by y prime. Right, and so
sorry for just cutting in again. And
yes,
just to see if I'm understanding this, it's sort of like we're recognizing that there is y's we can't and separate out easily, so we're figuring out what y prime is by essentially pulling out the y, figuring out y prime, plugging it all back in, and then solving for the y prime.
Yes, good, top notch. And it's going to take a little bit of practice, But once you kind of see that, oh, I just treat the y as if it's an x, and then I multiply by y prime because that's just what I do, then it won't be so bad. But it's getting into that habit that's tricky. So you differentiate x as we would normally, and then differentiate y, I'll say normally, kind of in quotes as well. Oh, it's really laggy today. And then, and can I say tack? Maybe multiply, and tack on a y prime. Yeah. So it just has that, and that's because of the chain rule, but you don't need to think of it as the chain rule because that's kind of tricky, but you do have to add on that y prime, and then you rearrange it and you solve for y prime. Solve for y prime, and then you have it, which is what you wanted to solve for. So, and then we also talked about, I'll do a little arrow here, implicit differentiation we used to find inverse functions. So inverse, or rather the derivatives, or yes, derivatives, the inverse trig functions. Derivatives. We did the proof of, I think, sine inverse or arcsine, and then the other proofs are similar. I noticed that I think the homework for inverse trig functions are actually going to show up in the 3.6 homework. In 3.6 homework, I think they just write HMWK. Anyways, I think that's where it was. So they've kind of bumped it till later, but that's okay. So just in case you're worried because you're not seeing it in 3.5, it'll be in 3.6. Okay. Promise to do more examples. We had a couple more examples on the handout. And then I also went back into an old final exam and grabbed the implicit diff, using the Maple term, the implicit differentiation question from the final exam. So we'll go through that one as well, just so we can kind of see what level we're expected to be working at. And then we'll move on to funner things. Logarithmic differentiation. That is fun. Okay, so let's see here. Grab. Oh, it's all in one. Great. So first we want to differentiate y equals 1 over the sine inverse. So good thing we have those derivatives laid out already of x. And then we want to find the derivative of x times arctan, which is tan inverse, right? Arctan of root x. So we'll start with a, of course. And you can use y prime if you want, because what we do, right, is we differentiate both sides. And so we have, I'm going to do d dx of y. Is d dx of 1 over sine inverse of x. Remember, because I have a hard time showing that I'm about to take the derivative any other way but the d dx, right? But then now in the next step, I'm going to write y prime. So, and they're equivalent, right? Especially so if I take the derivative of y, right, y to the power of 1 becomes 1y to the power of 1 minus 1, which is just going to go to 1, right? So it becomes 1 times y prime. So we're still doing that, except now we're just writing y prime. And then we had 1 over sine inverse of x. I know the derivative of sine inverse, but I have sine inverse to the -1 essentially, right? And so d dx of sine inverse of x to the -1, right, to bring that up top. Now I have a chain rule here because I have an outside function where it's to the power of -1, and then I have the inside function, which is arcsine of x. We know the derivative of arcsine, but by the chain rule, right, I have to take the derivative of the outside, evaluate it at the inside, times the derivative of the inside. So here we go. -1 times sine inverse of x, and I guess we don't have the brackets there, sine inverse x to the -1 minus 1 is -2. And then, just to kind of slow my roll here, I'm going to multiply by d dx of sine inverse of x. You could just jump straight to that 1 over root 1 minus, I think it's 1 minus, yeah, 1 minus x squared, right? You could go straight to that, but I'm going to hold up here sine inverse of x. And so here, this is the outside and multiplied by the inside. All right, it's going to be negative. So with that power of -2, I'm just going to bump it downstairs right away. And so I get -1 over sine inverse of x squared, because when I bring it downstairs, I can ditch that negative, times 1 over the root of 1 minus x squared. I'm technically multiplying by 1 the derivative of the inside of sine inverse, but we don't need to do that because x is just x, right? So if we had something bigger inside the sine inverse, then we would need to chain that on as well, right? But we don't because it's just x. So combining these, nothing left to do except combine these two. So -1 over, and it's not going to get very fancy, sine inverse of x squared times the root of 1 minus x squared. And there's nothing really left to do there. Okay. How about B? We have x. So f of x is x times the arctan of root x. All right. So f of x equals x times the arctan root x. So first, let's recognize that here the arctan of root x is going to be a chain rule, because now I've got a function inside a function, root x inside arctan. But then I also have a product rule, x times that. So x times a chain rule makes a product rule. So you'll want to do this methodically, right? I would probably start with the product rule, because from the product rule, it's going to tell you to find the derivative of that chain, arctan of root x. So, all right, let's see here. We like prime notation. F prime of x, let's do it, is the derivative of the first. So I'm going to start with the product rule. So maybe I'll do like a number 1 in here. And then move on to the chain rule. So my first term in the product is x, and the derivative of x is just 1. So I'll do 1 times, and then the second function, which is just arctan root x. The product rule we add, right? So plus, now I hold the first function steady, so x times the derivative of arctan of root x. So you can go straight for it, remembering that it's a chain rule. I'm gonna, again, just write out that I have to do that derivative, so times d dx of the arctan of root x. But like I said, if you want to, you can go straight to the next line. So, kind of simplifying here, 1 times the arctan of root x is just going to be arctan root x plus x times, okay, from last day, the derivative of tan inverse of x, which is arctan, is 1 over 1 plus x squared. Yep. So I'm going to put that in here and just kind of maybe put it up top. Oops. Up top here. And I'm just going to say tan inverse. This is arctan of x. Okay. So the derivative of the outside evaluated at the inside, which is root x, is going to be 1 over 1 plus root x squared, which is nice because that's going to make it just x, right? Times the derivative of the inside, so root x is 1/2 x to the negative 1/2, right? 1/2 minus 1 is negative 1/2. So now, okie dokie, here we go. I have that derivative of arctan root x. Okay. So now I can simplify a little bit, right? I can bring down this root x down to the denominator, remembering that I have to multiply it by 1 times x, but then I also, have this x up here multiplying in, right? And so we're going to be able to cancel some of these. Okay. The first term, arctan x, or arctan root x, sorry, it's just going to stay itself. And then we have plus x over 1 plus x times 2. I should have bumped that out front, but I forgot. 2 root x. Now, root x is, of course, x to the 1/2 and then x to the 1. So if I want to simplify this, because everything's being multiplied by root x, I actually end up with a root x up top, right? 1 minus 1/2. So here, these are going to cancel, and this is going to become root x. So now I can rewrite this as the arctan of root x plus root x over 2 times 1 plus x, or if you want to expand that to inside, that's totally fine too. X, well, I should say. And so that was kind of a combo of those inverse trig functions with kind of the chain rule, the product rule, not really implicit differentiation. So let's do an implicit differentiation here. Okay. So example, and I'll just clarify that this is an implicit diff question from an old final. So the question says, find the equation of the tangent line. Oh, always with finding the equation of the tangent line, right? But it involves finding the derivative and then finding the equation of the tangent line. So find the equation of the tangent line. Find the equation of the tangent line of, and here's our function. So this is kind of the level that we're expected to be playing at. 2xy equals x to the 3 plus y squared minus 1 at the point 1, 2. So on the left-hand side, let's remember that we have a product rule here, but otherwise everything looks pretty good, right? So just kind of recognize that you've got a product rule here, but nothing else crazy is going on, right? So if I want to take the derivative of this thing, and again, to show that I'm taking the derivative, I'll use d dx of 2xy is d dx of everything on the right-hand side, x to the 3 plus y to the 3 minus 1. So I'm going to treat 2x as my f, and then y as my g. That 2 can go with either the x or the y, but it just makes it easier if you keep it with the f, because then you've got a pure y. So if I take the derivative here, do I mean y squared? I do. I really, really do. Thank you. Do you know what's so funny? I did that in my notes as well. And then I went back and I fixed it. So why would I do it again? I just want it to be y to the 3. Oh my gosh. And good catch.
So I'm to understand that this is just a thing we're going to have to deal with if, when doing math. Just, oh yeah, that number is just going over there. No, it doesn't.
Yeah, yeah. Don't listen to me.
I don't think we'd have a very good chance of passing the course if we don't.
Yeah. Yeah, so I managed to make the same mistake twice. Impressive, right? All right. That's all right. Okay, so we need to do the product rule on the left-hand side. So the derivative of the first is just going to be the derivative of 2x, which is just 2, right? So 2 times y. I should put the 2 in brackets times y. And then now I hold the 2x steady times the derivative of y. Well, if I take the derivative of y, it just becomes 1, and then I have to multiply by y prime, right? So usually we just go for to write the y prime. Okay, manage the left-hand side. Now let's see if I can keep it straight on the right-hand side. So if I take the derivative of x to the 3, right, it's got an x, so it's just normal, right? So we know that's 3x squared. Now for the y squared, right, I take the derivative of the y. Normally, I say normally in air quotes, right, because we're just pretending that we're just taking the derivative of y. So we become 2y times, and then we have to tack on that y prime. And then, of course, the derivative of minus 1 is 0, so minus 0. You don't have to write it out, but sometimes it's nice to see where stuff went. Okay, so now we're going to rearrange and solve for y prime, right? But there's no more derivatives that we have to find. So because we've already kind of found them in y prime, right? And so what we're going to do, I'm going to move all my y prime terms over to the left-hand side and anything else to the right-hand side. So I get 2x y prime minus 2y y prime is 3x squared minus 2y. Pulling out the common factor of y prime, I get y prime times 2x minus 2y is 3x squared minus 2y. Right-hand side didn't change. So then I can solve for y prime, and maybe I should put it on its own line here. Y prime is then 3x squared minus 2y over 2x minus 2y, and I guess I don't need those brackets because they're not really doing anything. Great. Now, here's where if you were solving for the overall derivative, right, now we're going to use the derivative to find the slope of the tangent line at 1, 2. So we're curious about a specific point, whereas sometimes we might just we would just leave it as, because we don't know what y is. So we would just leave it like this, right? So this is our derivative. Sorry, I was thinking about another thing that we're going to do later, but yeah, I'll be quiet. No, I won't. I'll keep talking. So this is our overall derivative. This is the slope of the tangent line at any point on this curve, xy point on the curve. So at the point 1, 2, right, x equals 1 and y equals 2, we can just plug those into y prime, right? So then y prime is 3 times 1 squared minus 2 times 2 over 2 times 1 minus 2 times 2. 3 minus 4 makes -1, and then 2 minus 4 makes -2. So -1 over -2 puts me at 1/2. So that's going to be, so here, this is the y prime. Sometimes, I'll just make a note here that sometimes they'll use the vertical bar and then say something like at 1, 2. And this just means we've seen it before, but I rarely use it. But just in case you're seeing it kind of around town, you've got this vertical bar evaluated at 1, 2, and it just means you're plugging in x is 1 and y is 2 into this thing. Okay, so now we know the slope at 1, 2 is positive 1/2. So we've got this slight incline, positive incline. Positive is an incline. Now for the tangent line, the equation of the tangent line, we're going to be so good at constructing lines by the end of this course. Well, we have y minus y naught is m times x minus x naught in general. Y minus 2 in this case is 1/2 times x minus 1. So then y is 1/2 x minus 1/2 plus 2, and I'm just going to force it to have that common denominator of 2 right away by multiplying by 2 over 2. And I want to keep it, I just need one more line, ironically, because we're making lines. So let me just bump it up so I can have. So I had to force a common denominator. So now I get -1 + 4 over 2, putting me at an overall line of y equals 1/2 x minus 3 over 2.
Plus 3 over 2.
Another error in my notes. Man, I must have been sloppy. There. Good thing you guys are on it. All right. Good. Any questions before we move on? So we will use implicit differentiation in the next sections as well. So of course, we're not just kind of ditching it, we're going to use it. But any questions before we move on to the next section? No? All good.
Crop to mind.
We'll see. Yeah, it helps if you, if you've seen some other problems, but let's do 3.6. I promise it's a little bit more fun than this. So 3.6 is on derivatives of logarithmic functions. So chapter 3 is really tricky because we're developing all these skills that we need to be able to take derivatives. Oh, in case you haven't noticed, I made 3.7 because we won't really have time to do it in class. But it's just kind of applications of derivatives. So in physics, in biology, in economics, right? So it has all these applications, of course, and that's why everyone has to take this course. But I just kind of left them and I just posted some notes to have on the side. But I labeled it optional, and then I'll use, if you want to try that assignment, I made it nice and short. And I'll use it as a bonus assignment to bump up your grade if you want. So, but it's totally optional. So let's do derivatives of a logarithmic functions. Way easier to just say logs. So we can develop, and I do want to kind of take a little bit of time to develop the derivative of the log, because I think it's kind of fun to see where it came from. But then, of course, like everything else, you can just use the property that we land on in the end, right? And so, but it's nice to see where it came from. So let's just summarize here. To find the derivative, to find the derivative of, I'm just going to say of a log function, logarithmic, too long, function, we use implicit differentiation, which I'm just going to say diff, along with the fact that we already know that the derivative d dx of b to the x is b to the x times the log of b from section 3.4, right? So we developed that, and we used it definitely in that weird one that we went through last day. Turned out it wasn't that weird, but I don't know, when first faced with it, it was weird. So yeah, so we're going to use this derivative to develop the derivative of a log. So let's see here. Here's the proof. First, we're going to let y be the log base b of x, right? Just allowing for any log base. By definition, then, we can say that b to the power of y equals x. Oops. Then b to the power of y equals x. And that's just by log laws. So now notice that I have a y baked in here, right? And so this is an implicit function. It's going to be without going back to where we started, right? That's not a very good direction to go. Going back, okay, I can solve for y, sure, but we're trying to kind of get out of that and figure out how to find the derivative of this thing. So we can use implicit differentiation. So we can differentiate with respect to x. So then I have, okay, well, I know the derivative of b to the y, right? The derivative of b to the x with respect to x is b to the x times the log of b. But now I have a y, so then after I've taken the derivative of the y, I have to multiply by y prime. So I get b to the y times the log of b times y prime. And then the derivative of x on the right-hand side is just going to be 1. Right? So now solve for y prime. Well, y prime is going to be 1 over b to the y times the log of b. But how about this? Well, b to the y is x. So now, let's see here. Whee. I can replace that b to the y with just an x. So then y prime is 1 over x times the log of b. Which brings us to that definition. Let's see if I can do that. Oops, wrong one. Here. Which brings us to this one. So the derivative of log, so the log of any base of x is 1 over x times the log of b. Now, what's really, really nice is what if you take the log base e, right? Well, log base e is ln, but the ln of e is 1, right? So we have this special case where the derivative of the natural log is just 1 over x. So we can let b be e, right? So then log base b becomes log base e, which is just ln, or I do a little script ln. Should probably write it the same. So notice that if you have the d dx of log base e of x is 1 over x times the ln of e, but that's going to be 1 over x since the ln of e is 1. So that's really nice, right? Because now we have the special case where if we take the derivative of the natural log, it's just going to be 1 over x. So let's grab that one. So here, this is going to be the reason that we prefer ln over any other log base. So this is why we will prefer ln over any other log base. Just because it has that nice property of just 1 over x is the derivative. Okay. Let's do an example. I'm trying to get in the habit of just doing that. Okay. So let us do example 1. So what happens here? So now I'm taking, so I want to differentiate y equals the ln of x to the 3 plus 1. So now I have x to the 3 plus 1 inside the ln function. So again, I have this chain rule, but nothing else going on, right? So I can find y prime, I'll just use prime notation, by this property here. If I have the ln on the outside, well, the outside, the derivative of the outside is 1 over x, but evaluated at the inside, which is x to the 3 plus 1, right? So then it becomes 1 over x to the 3 plus 1 times the derivative of x to the 3 plus 1, right? So we get 1 over x to the 3 plus 1 times, now the derivative of x to the 3 plus 1 is just going to be 3x squared. And I have, I'll confess right away because it might come up. I have a really bad habit of forgetting to tack on that power. I don't know why. I don't know why it is, but I'll bring the 3 down and then I forget to tack on the square and it makes a mess. But that's okay.
Oh, it's because you've already moved the 3. Yes, the thing that was there is over here now.
Yeah, it's over. It's over. I'm over it. And that's it, right? Then we have the derivative. So that's why it's really nice to take the derivatives of the natural log. And I can rewrite it as 3x squared over x to the 3 plus 1 if I want to, but I don't have to. So what we've used here is the chain rule. There is a little blurb on the handout here. This one, but I don't really want to bring it in because it's just kind of like, okay, well, I guess we can, no, it's kind of a special case. I don't want you to get hung up on special cases, right? So if you've got the chain rule, but we're going to do kind of more weird things like example 5, for example, right? So how about for completeness, I'll bring in this blurb, but this is kind of using the chain rule with ln. Let's do another example instead. Oh my gosh. So here we have another chain rule, right? I have the ln on the outside and I have sine x on the inside. So, all right, here we go. So the d dx of the ln of sine x. Notice that there's no left and right hand sides, and that's okay. I can just say that this is equal to, right, 1 over sine x times the derivative of sine x, which is cos x. Again, you're fine to just leave it as cos x over sine x, or if you kind of think, oh, that must be, I must be able to simplify that as something, right, then it's the cotangent of x. Just to clean it up a bit. And that's it. How about example 3? So notice that these are all itty bitty compared to what we have been doing. Okay. So now I have the chain rule again, but now I have the log of x on the inside of the square root. Right? So if I want to find f prime of x, then that's going to be the derivative of the outside, which is the ln of x to the 1/2. So I have to bring that 1/2 down, evaluate it at the inside, ln of x to the negative 1/2 times the derivative of the inside, which is 1 over x. Not bad. We can
Quick
clean this
question.
up a little bit. Oh, say that again.
ln to the 1/2, but you wrote down negative 1/2?
Yeah, I'm going straight for the derivative, not messing around. So what I did here is I said, well, this is the same as...
Okay. Yeah, I remember now. It's 1 minus, or the number minus 1, which would make a negative. Okay.
Yeah, the square root is one that we do so often that I just jump to the minus 1/2 as the new power. But it is just 1 minus, or sorry, 1/2 minus 1. That's what it is. Okay, so now I can just kind of do a little mashup here, and it becomes 1 over 2 x log x, just so we don't get confused of what's inside the log and what's outside. Oh, to the, no wonder. 2x, the root of log x. I bumped it down and I have to take the square root. Okay. How about another one? Example 4. Now we need to make sure, because we have log base 10, so f of x is log base 10 of 2 plus sine x. So now we need to go back to something that's not ln, right? So the log base 10 of something, remember from before, is, so now b is, oh, it's just catching up. B is 10. Right, so now you have 1 over x times the log of 10, or the natural log of 10. So it's still the natural log under there, but b is 10. Okay. So going straight for the derivative, f prime of x is 1 over, and maybe what I'll do is I'll say d dx of log base b of x is 1 over x times the ln of b. just as a reminder. So then x, right, the derivative of the outside is log base 10, evaluated at the inside. So x is still going to be 2 plus sine x. So I'm going to do 2 plus sine x down here times the log of b, the natural log of b, which is the natural log of 10. That's the derivative of the outside, right? So here, this is the outside. Now I want to find the derivative of the inside. The derivative of 2 plus sine x is just going to be cos x. So times cos x, and this is the inside. Now, since you're just multiplying, shouldn't say just, but since you're just, well, I did it again. You are just multiplying, fine. We can just write these on top of each other. So cos x, and there's really no simplification that we can do here, right? Times 2 plus sine x times the natural log of 10. Want to do a big one? We're going to anyways, but. So these have all been.
Gotta keep us with that illusion of choice.
Yeah, we're going to do it anyways. So here we go. Example 5. If you kind of study it, it's a little bit bigger. In fact, it's big enough it warrants its own fresh page here. Why is that? So I do have the ln, which is nice, right? Because I know the derivative of ln is just 1 over x. But in this case, x happens to be a quotient rule, right? And so the derivative of the inside is going to be what's kind of messy, right? And so here we've got a quotient rule. Breaking down the quotient rule, I also have a chain rule inside the quotient rule. Right? Okay, here we go. And then I have this ln on the outside, so that's another chain rule. So I want to give you guys kind of 2 minutes to try your hand at breaking this down, and then of course we'll go through it. Maybe I'll pause this. Okay, so definitely the easiest thing to do is taking the derivative of the log. So and we kind of start on the outside and work our way in, right? And so let's see here. I'm just going to write it out. I'm going to write out the question on the left-hand side and then equals, and then work on the right-hand side. So I'm going to have d dx of the natural log of x plus 1 over the root of x minus 2. And I'll try to give myself lots of space. In fact, move this equal sign over. Lots of space on the right-hand side. I anticipate I'll need it. Okay, the derivative of the outside is easy enough, I think. 1 over, but then x plus 1 over the root of x minus 2. Then I'm going to, so just to kind of take it step by step, I'm going to multiply by the inside. So d dx, or sorry, the derivative of the inside of x plus 1 over the root of x minus 2. So I'm going to save that for the next step. I also want to remember that 1 over a fraction is really just a fraction over a fraction. So I can actually simplify this 1 over 1 over x plus 1 over the root of x plus 2. Flip and multiply, I can simplify this just to save a little bit of space here. It becomes the root of x minus 2 over x plus 1. And then that's all times. Okay, here we go. The quotient rule, I'll start with the quotient rule. And I'll incorporate that chain rule into my quotient rule, because of course when I take the derivative of the denominator, that's a chain rule. So the derivative of the top one is just 1 times the denominator, the root of x minus 2. So that's fine. For the quotient rule, we subtract, right? So then minus, and then x plus 1 stays the same, right? The first term stays the same. And then I have to multiply by the derivative of the denominator, which is going to be 1/2 times x minus 2 to the negative 1/2 times 1. Because this here is the chain rule. And then that's all over the root of x minus 2 squared. There are no more derivatives. We're done with the derivatives. So now it's a matter of simplifying, right? And so what can we do? Well, I'll rewrite this x minus 2 to the negative 1/2. I'll rewrite that in the denominator and see what happens. Or what else did we do here? Or what else did I do, I should say. Oh, okay. The root of x minus 2 squared, but then that's also being multiplied by the root of x minus 2 in the numerator. So I could just cancel one of these root x minus 2 with this power of 2. So I would still have the root of x minus 2 in the denominator. Does that clean anything up? What did I do here? X minus 2. Okay. Yeah, I think that's what I'll do. There are a couple of ways that you could go about doing it, right? You could bring in this root x minus 2 and multiply it by this root x minus 2 in the numerator. And then you also have root x minus 2 over root x minus 2, right? Once you bump this x minus 2 to the negative 1/2 to the denominator, maybe that's a cleaner way to go. Okay, here we go. So what I'm going to do is I'm just going to multiply this root x minus 2 through the numerator, but also the x plus 1 through the denominator. All right, but like I said, there are a couple of different routes that you could go depending on what you think is easier to simplify, but it's kind of a beast to simplify this thing, so that's okay. I'm going to rewrite my roots as powers of 1/2, just because in order to simplify, I'm going to need to work with the exponents anyways, so it just makes it nicer to look at. So x minus 2 to the 1/2 times x minus 2 to the 1/2 minus x plus 1, x minus 2, I'll bring it in now, x minus 2 to the 1/2 over 2 times x minus 2 to the 1/2. And then that's all over x plus 1 times x minus 2, right? The root of x minus 2 squared is just x minus 2. Okay. All right. This looks better, right? Because now I can just cancel the x minus 2 to the 1/2. There. And I can also, oops, simplify this. The root of x minus 2 times the root of x minus 2 is, of course, just x minus 2. So I have x minus 2 minus x plus 1 over 2. I'm going to leave a little bit of room because I'm going to force that common denominator now. X plus 1 over 2. And then up here, I'll force that common denominator of 2, just so I'll be able to combine those. Kind of an afterthought. Over x plus 1 times x minus 2. Expanding this 2 inside, right? And then also expanding this negative inside, I end up at 2x minus 4 minus x minus 1 all over 2 over x plus 1 times x minus 2. Cool. Things are simplifying. Remember that you're going to have a fraction over a fraction again, right? So you can flip and multiply as long as you kind of think of this as over 1, right? So then where do we get to? 2x minus x is just x. Negative 4 minus 1 is minus 5 over 2 times 1 over x plus 1 times x minus 2. I wouldn't really bother, or I wouldn't bother expanding this because, well, one, I hate factoring. So if I ended up having to use this later, I would rather have it factored already. And so I like to keep them factored. But also, I don't see a way that I can cancel x minus 5, right? Just kind of glancing ahead. If there was an obvious way to cancel x minus 5, then of course go for it, but there isn't. So then we just end up with x minus 5 over 2 times x plus 1 times x minus 2. Great. So that's a big question, right? We incorporate the chain rule, the quotient rule, and the logs, right? So, and the chain rule again, I guess. So we can establish the derivative of the natural log of the absolute value of x. So just kind of anything goes for x. So here we go. Because remember, we can't take the log of a negative number, but we can take the log of the absolute value of x. So here, and we're basically going to prove the statement that's down below, right? That the natural log of the absolute value of x is just 1 over x. So we have to remember that f of x is, if we're taking the log of the absolute value of x, then it depends on what x is. So it's the natural log of x, just plain and simple, if x is greater than 0. It's going to be the natural log of negative x if x is less than 0. And that's just because of how the absolute value behaves, right? We don't just drop the negative. If it's negative, we take the negative of that negative, and that makes it positive, right? But now we can easily find the derivative of this thing, right? And so here, our derivative is also going to be a piecewise defined function, right? The derivative of log x is just 1 over x if x is larger than 0. Oh, I'll keep going. So then the derivative of the natural log of negative x, right? Remember, so now we have 1 over negative x, but then we need to multiply by the derivative of the inside, which is -1. And this is if x is less than 0, which, and maybe I'll just bump this over just a smidge here. Oops. Now I've done it. -1 over negative x just puts me on 1 over x. So then we have, in fact, established, oops, that the derivative of the log of the absolute value of x is just 1 over x for all values of x, except when x is 0, right? This is true for all x not equal to 0. Let's just say it like that, okay? Because we can't divide by 0. Good. How about you, Carly? Do you need a little brain break? All right. Let's do it then. Okay. I might start it on a fresh page. Let me see here. Get the lay of the land. Okay. So you didn't miss anything. It's just 1 over x for everything. But now it's established. And I was checking if you guys wanted a break, or should we just go for it?
Well, I just got back, so I'm good.
Let's do it. Let's do it to it. The reason that, or a tool that we're going to use is the fact that the natural log is so easy to differentiate, right? And so we can also think back to log laws, right? Things like the log of AB, I can rewrite as the log of A plus the log of B, right? Also, the log of A over B is the log of A minus the log of B. And especially the log of A to the power of B is the same as B times the log of A, right? And so, and maybe I should preface this with something. We can combine I'm going to say the simplicity of the derivative of the natural log with the log laws. So we can combine the simplicity of d dx log x equals 1 over x with the log laws, which kind of these are the most important ones that we'll be using. Can't think of any others right now. Right, and so we can combine these log laws with the derivative. So here, A times B, you would need the product rule, right? Here you would need the quotient rule, and here you would need the power rule. But what if you're able to just rewrite it as the log of A plus the log of B and then take the derivative, right? So A couple of caveats, but it's going to be a tool for us to be able to simplify a complicated function. So we can combine these with the log laws to find the derivatives of complicated functions. And so that's where we get this logarithmic differentiation, which is on the next page. Stated up top here. Logarithmic differentiation. So logarithmic differentiation, or let's just call it log diff, can be used to simplify complicated functions, just to kind of introduce it. It can be used to simplify complicated functions. And I've got the steps there in the handout. Okay. So what you're going to do is, if you see, and we'll do an example, if you see a big nasty equation, and the key is where the product rule combined with maybe a little bit of chain rule, or the quotient rule maybe with a little bit of chain rule, where those won't suffice, right? Then maybe start to think logarithmic differentiation. But I don't want it to be your go-to if something kind of simpler would work, right? So if you see a big nasty equation, probably use logarithmic differentiation. And we'll talk about another case where you might have to use it to simplify. But so the idea is you're going to take the log of both sides. Because ln is so nice, right? The derivative of ln is 1 over x. We're going to just use ln. You can use any base, but we're going to use ln. Maybe I'll add that in here. Oh, it is saying that the natural logarithms. Not messing around here. You could use any base, but of course we're going to use the ln. So then if you take the log of both sides, then you can rearrange it using those log laws that we developed, right? And so if those haven't been kind of committed to kind of second nature, now's the time. Because then once you've rearranged those logs, then you can differentiate implicitly, of course. And then you can solve it for y prime. What does that look like? Here we go. Hey, it glitched out. It needed a break. How about that? Okay. So let's have a look at this example here. What you want to do is you want to kind of survey the scene and see what you would need to do, right? First, I see I have a chain rule here. I have, I have another chain rule here. I have a product rule in the numerator. But then I have it all wrapped up in a quotient rule. Yikes. No, thank you. Right? You could, just taking your time and really being careful, you absolutely could work through this without logarithmic differentiation, right? It's just going to be a lot easier if we take the log of this thing and then differentiate. So we could solve this without logarithmic differentiation, right? And that might be a fun exercise on the side, maybe later. Not for me, for you. So you could solve this without logarithmic differentiation. But it will be much simpler if we take the logs. But if it will be much simpler if we take the logs. Right, so if we apply logarithmic differentiation. So let's see here. If I take, so I'll outline these steps. Steps 1, I have to take the log of both sides. And of course, when I say log, I mean ln. So where does that put me? Well, it puts me at the, you don't want to forget about the log of y, right? ln of y. So you have to take it up both sides. So here we go. We get, oops, ln of y equals the ln, and I'm just going to write the whole big mumbo jumbo inside before I go ahead and break it up. X to the 3/4 times the root of x squared plus 1 over 3x plus 2 all to the power of 5. Remembering our log laws, right? If we have division inside here, then I'm going to rewrite it as a subtraction of the logs, right? And so, and maybe what I'll do is, because it's going to get quite large, I'm going to bump it over to the left as much as I can here. Should have done that already. So here, I'm going to write it as the log of the numerator minus the log of the denominator, just from the log laws. So this becomes the ln of x to the 3/4 times the root of x squared plus 1 minus the log of 3x plus 2 to the power of 5. And maybe I'll clarify here. The log of a over b is the log of a minus the log of b. So now there is kind of, I'll parking lot this 3x plus 2 to the 5 for a little bit, and I'll deal with this product, right? And so this becomes, if it's a product inside, then I'm adding those logs when I break them up. So now I have the log of x to the 3/4 plus the log of the root of x squared plus 1 minus the log of 3x plus 2 to the power of 5. And this is from the log of ab is the log of a plus the log of b. Okay. So you want to do your multiplication and your division inside the logs, break those out first, and then our next step is going to be, and it doesn't matter which one you do first, it'll work out either way. So now we want to deal with these exponents, right? Remember the log of a to the b is the same as b times log a. So here, this is going to get even better, right? X to the 3/4 becomes 3/4 times the log of x plus 1/2 times the log of x squared plus 1 minus 5 times the log of 3x plus 2. Right, and this is because the log of a to the b is b times log a. Right, and that's how we bring those powers down. Is shaping up. Remembering that the left-hand side is still equal to the log of y, right? So when we take the derivative, which is in the next step with respect to x, we still have to use implicit differentiation and multiply by our y prime. But besides that, there's no y's on the right-hand side, so we're kind of free to go. Step 2 is to differentiate implicitly with respect to x. So, okay, the derivative of the log of y is 1 over y times y prime. And then the derivative of, so now I'm on the right-hand side, the derivative of 3 over 4 times the log of x is just 3 over 4 times the log of x. Oops, sorry, 1 over x. Kind of moving through these, right? Because we've already worked with finding the derivatives of these logs with the chain rules inside. So now I have plus 1/2. Remember, for taking the derivative, those constants just get bumped and multiply the derivative. So times 1 over x squared plus 1 times the derivative of the inside, right? Don't want to forget about that 2x. Minus 5 times 1 over 3x plus 2 times 3. Okay. Let's simplify the right-hand side for a little bit. I can also put y prime over y if I want to. First term becomes 3 over 4x plus 2x over 2 times x squared plus 1. I can cancel these 2's, right? So I'm going to end up at x over x squared plus 1 minus 5 times 3 is 15. And then there's nothing I can cancel with, right? Because I need to have a common factor. So I can't cancel anything. So it's just minus 15 over 3x plus 2. Nice. Notice that we have solved for y prime over y, right? But now we want to solve for y prime. And this is where we get into what we did last day, right? Where, okay, we know what y is, and that's what I wanted to do earlier. It didn't work, but now because we know what y is, then I can plug it in, and then I have the derivative. So step 3 is to solve for y prime. I'm not going to bother putting it over a common denominator because it would get really, really messy and big. So I'm just going to keep them as individual terms. So what I have is I have y prime is y times the right-hand side, right? Multiplying that y over. So I get 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. Here, we know y from before, right? So now I'm going to make that substitution and then we'll be done. So then y prime is y, which was x to the 3 times the root of x squared plus 1. I'm not going to scroll up because it lags so much.
X to the 3 divided by 4. Just to.
Haha. I need you guys proofreading my notes. And here I am. I'm not going to scroll because it's too laggy. Should have scrolled. Thank you. 3/4. Let's see if I have the rest over 3x plus 2 to the 5. Cool, thanks. Good. And then I'm just going to keep it as that's all times because this would be a real mess to untangle. So once you've plugged in the y, typically we're going to leave it. So then times 3/4x plus x over x squared plus 1 minus 15 over 3x plus 2. We did it. Was it better than quotient rules involving chain rules, involving product rules, probably involving chain rules again? I can't remember. Maybe, probably, right? So it made it, the derivatives themselves were quite a bit simpler, right? And so that's why we would use it. I do want to make a note here. Right, so here, you don't want to use logarithmic differentiation for kind of simpler problems, right? Where you could use the product rule and the quotient rule maybe. So do not use logarithmic differentiation if the product or quotient rule would suffice. That's just a little heads up, right? You don't want to go through working with those log laws and then when it's kind of an easy derivative to find anyways.
Yeah, just looking at it, and my mind's going like, yeah, if you have to use the log laws, if you're having to do like 4 different jumps.
Yeah, but
if there's like 1 or 2, it's like, yeah, you can do that easily enough.
Yeah, because those log laws take a little bit of effort too, right? So it's like, yeah, you want to find a trade-off where it's like, okay, here I'm going to apply the logs and then it'll be easier. But yeah, that's just kind of a rule of thumb. If it's this big, massive thing, just throw some logs on there and see what happens. Logs only help you though if you're multiplying or dividing, right? So because there's no log laws for addition and subtraction, we end up adding and subtracting, but so a little bit finicky there. So there's a little blurb on the handout that I'll pull in here because depending on the situation, right, we might have exponents and bases. So here, if you have b to the power of n, of course, if b and n are constants, and that's kind of boring, the derivative of a constant is 0. If you have some kind of exponent, then you can just use the power rule, right, and bring down that exponent, and then maybe the chain rule. And then lastly, if you have b to the power of a function, which we dealt with, I think last day, maybe the day before, you can still solve that without logarithmic differentiation. So here, you don't actually need, for these kind of situations, you don't need logarithmic differentiation. And then here, there's an H missing, logarithmic. Maybe it's another way of, it probably is. But so here's the situation. If you have a function and in its power you have another function, then you can use logarithmic differentiation. In fact, that's probably the easiest way to deal with that. So here I'll say another scenario. So scenario 1, you have a really complicated function. Right? You apply the log laws, do it. Scenario 2, you have a function to the power of another function. Then you're going to use log laws as well. So if we have a function, with a variable base and variable exponent, which looks like f of x to the power of g of x, right? So a function to the power of a function. So if we have that, we use, and this should be colon, we use logarithmic, I'll even spell it out here, logarithmic differentiation to find the derivative. Okay. For example, we've got example 8. If I want to differentiate x to the root of x, so now I have f of x as the base, but also g of x as the exponent. So now the easiest way to, so just like when we were solving for x in the exponent, right, the easiest way to solve for that is to take the natural log or any log, right? But for us, because we're going to take the derivative, we're going to use the natural log. So we take the log of both sides again. So we get the ln of y equals the ln of x to the root of x. So I'm not taking the derivative quite yet. I'm going to simplify the right-hand side. I'll just write out the left-hand side. I can bring that root of x down, down front. I got caught up in root of x sounding like rutabaga. Doesn't matter. Root of x times the log of x. So now we've got this really cute product rule. Not bad, right? Well, and I guess a chain rule here, but it's itty bitty. So it's not really a chain rule because it's x to the 1/2. So it's really just a power rule, but whenever I see a root, I like to think of it as a chain rule, chain/power rule. Derivative of the inside there is just 1, right? So it doesn't really count.
Well, if you think about it too much, the power rule is just a chain rule.
Sure is. Yeah. You're just multiplying by 1 all over the place. So technically, yes, it is still the chain rule, but we can get around it. Yeah. Yeah, I feel like all we would really need is the chain rule. We should just start with the chain rule, but that is a little bit much.
There's reasons why you start with your times tables as opposed to just starting straight multiplication.
Probably. Yeah. Yeah, we ease into it. Okay, so now if I take the derivative of this thing, which I will show by just writing d dx's around both sides. So now I'm taking d dx of the log of y is the d dx of the root x times the log of x, right? Just to kind of show that now I'm going to start taking the derivative. Well, here we go. Log of y is implicit with respect to x, right? But it becomes 1 over y times y prime, of course. And then I have the product rule. The derivative of the first term is 1/2. Can I just write the root of x underneath maybe? No, I'll do x to the negative 1/2 here. Doesn't matter if you want to bring it down right away, that's totally fine. Times the second function, which is the log of x, plus the root of x, which is the first term, times the derivative of the second function, which is now 1 over x. So let's simplify this thing a little bit. Here I have x to the power of 1. Here I have a power of 1/2. I can actually combine these, right? A couple of ways you can think about it. You could break up x as the root of x times the root of x, and then cancel that root in the numerator. Or you can use exponent laws if you want to. So we get y prime over y is the log of x over 2 root x plus 1 over root x. Right? However you want to cancel that is fine. I am going to force a common denominator here. All I'm missing is 2, and then I can have 2 root x as my common denominator. So the second term I'm going to multiply by 2 over 2. So I have y prime over y is the log of x plus 2 over the 2 root x, that common 2 root x. Now I want to solve for y prime, right, by bringing that y and multiplying everything by y. I didn't break down the steps. No, I didn't. That's okay. Y prime is y times this whole thing, the log of x plus 2 over 2 root x. But we know that y is x to the root of x from before. This time it's a nice, easy equation to write, so I'm just going to write it out there. Before it was so big. Y prime then is x root x times the log of x plus 2 over 2 root x. Good. Did it. There is that one, so the number e as a limit. I have the proof. We're not going to do it. I'm just going to say it here. If you want, I'm sure the proof itself is in the textbook, but let's just kind of ignore it, right? It's stated here, so we can just use it as a fact, but let's leave well enough alone. We'll consider it done. So this stuff will be on the test, but of course it's the only thing that you won't have seen on a quiz. So that might be nice. I am working on a practice test, but I don't know if it's going to be done. I think probably realistically Sunday.
And give us the practice test after we're done the actual test.
Yeah, yeah. Wouldn't this have been so good? Yeah. No, you'll have the practice test, but and that's sort of why I bumped the quiz until because are you able to go back into the quizzes after you've written them, or are they closed? How does it work?
I'll check.
I guess I could stop this recording.